Welcome to an example on how to find the local maximum or local minimum of a function, also called extrema. We're going to try to find the local minimum of the function y equals x cubed minus 4x plus 7. And you can see it on the graph here. And we can see that the function has a local maximum and a local minimum. So we're going to find all critical points of the function and then determine, using the first derivative test, if they are maximum or minimum. And then we'll find the value of the minimum. So we'll start by taking the derivative of the function. Of course, the derivative of y is dy dx. By the power rule, we know the derivative of x cubed is 3x squared. We bring the 3 down and then we subtract 1 from the power. The derivative of minus 4x is negative 4. And then 7 does not have the derivative is 0, but it doesn't depend on x, so it doesn't affect the slope of the function at all. Now let's say you have any random function or line or anything. You can have a line that is tangent to the curve, which means that it only touches the curve at one point. It will never intersect it again. And you can have that at any point on the curve. And instantaneously it will have the same slope as the green line will have the same slope as the red curve. The green line on the top has 0 slope because it is tangent to a maximum point. Right there, that is where the slope is changing from positive to negative. So we're going to set the derivative, which is 3x squared minus 4, equal to 0, because we know the derivative is the slope, so we're going to find out where that equals 0 so we can find the maximum and the minimum points of the function. This is just evaluating algebraically, heading 4 to both sides, dividing each side by 3. We have 4/3 equals x squared. The square root of that is about plus or minus 1.2. Now for the first derivative test, we're going to test a value above and below each critical point to see if the derivative is positive or negative on each side of the critical point, because that will tell us if the slope is positive or negative on each side of the critical point. So we'll start off with negative 2. Plug that into the derivative. 3 times the negative 2 squared minus 4 is 8. So that is a positive number. Now we're going to try one above 1.2. We'll try 0. We need to make sure that we don't choose a point that is above our other critical point of positive 1.2, or else that will give us bad information. So evaluate that. It's negative 4, and the derivative is negative. So we know that the derivative is positive before the critical point, negative 1.2, and negative after the critical point, negative 1.2. So we're going to use a number line to help us visualize what's happening. Right here we have our critical point at about negative 1.2. We know it's positive to the left of it, which means the function has a positive slope, and the slope is positive before the critical point. And we know it's negative after the critical point, which means the function has a negative slope. Now you can imagine if you were to connect these two lines and make them into a curve, it would look like a maximum point. And that's what it is. That's what the first derivative test does. So we know that at the critical point negative 1.2, there's a maximum. So now we're going to test a value that is below the other critical point of 1.2 and also above the critical point of 1.2. We'll start with x equals 1. And we need to make sure that, again, that we're not choosing a critical point, a testing value that is below the other critical point of negative 1.2. So we evaluate this and we find that equals negative 1, negative slope before the critical point of 1.2. And now we're going to test a value that's above 1.2. We'll do x equals 2. And evaluate the derivative at that point. It is 8. And that is positive. So there's a positive slope after the critical point of 1.2. We'll start with our number line again. Find the critical point on it. We know that to the left of it, the slope is negative, which is a downward, a decreasing function. And to the right of it, it's positive, an increasing function. Now again, you can look as if you were going to connect those two lines. It would look like a minimum. And that's what the first derivative test is. So we know there's a minimum at 1.2. Now we have this function again. So if we plug 1.2 into the function, the original function, not the derivative, then we can find the value of the local minimum. And y is about 3.9. So in conclusion, we have a local minimum of y equal to 3.9 at x equals 1.2. And here's our graph, that part of the graph that has the minimum on it. You can see right there is where it is, right about 1.2 and also 3.9 on the y.